Well, let's pick up from where I was before the break. What we've covered so far is pretty much a review of things that I've talked about in previous seminars at APEC. Where we stand right now is single test signal injection, either voltage or current, delivers a block diagram that includes the H0, which is one of the non-idealities, namely direct forward transmission, the wrong direction, so to speak, through the feedback path, which provides a non-zero output, even though the forward path gain goes to zero at infinite frequency. The limitation of that approach is that it requires an ideal injection point, which of course never exists in a real circuit model. So from here on, we're going to go into some new stuff. Dual test signal injection, both voltage and current simultaneously, can deliver a block diagram that includes all the non-idealities, not only the H0, but also reverse transmission through the forward path. That's backwards in the forward path. And the usual conclusion about that is, well, that's always negligible compared to the transmission in the forward direction. That, of course, is true at low frequencies. But at high frequencies, the forward gain drops off. And in fact, the loop gain ultimately crosses over unity and gets to be less than 1. In other words, the forward path tends to become a passive network rather than an active network. So the transmission in the two directions easily can be comparable at high frequencies. And this is trouble because just the place that we want to know the accurate answers is in the neighborhood of loop gain crossover, because that's what determines how the closed loop response drops off. It determines whether there's significant peaking and ultimately determines whether it even goes unstable. So the neighborhood of crossover is just where we want to get accurate results, and that's where these normal assumptions of unidirectional flow in the two boxes breaks down. So that's where it's important to know what a better model is. Dual test injection of both voltage and current, as we're going to see, also works for a non-ideal injection point, which is the only kind you actually have available in the real case. Not only that, it's all of it is implemented in the Intersoft ICAP circuit simulator. And it gives all the results you need, and we'll see some examples of what they are. Now, we've already seen what the failing is of single injection. That is, a non-ideal voltage injection point implies that when Vy is null, what's the error voltage, the error current is not necessarily null, and vice versa for the current injection point. So if you want to make the H infinity equal to the reciprocal feedback ratio, which is where you have the proper interpretation of these quantities that you want to have for design purposes, what we have to do is find a way to null simultaneously both the error voltage and the error current. Now, first, I want to expand the horizon considerably from the particular examples that I've used up to now. We've already seen that a non-ideal injection point gives you some different answers from an ideal injection point. And there's an interesting consequence of that. That means that you get different sets of second-level transfer functions for different injection points, but if you plug them into the appropriate formula, they all give the same answer for the final closed-loop gain. That's fortunate. Otherwise, something is seriously wrong. But it's kind of miraculous that whatever injection point you choose, even a random injection point, gives you different sets of the T, Tn, H0, H infinity, but when you plug them into the basic formula, you get exactly the same value of H every time. Here's a generalization of that. It doesn't even have to be a circuit that has any identifiable feedback in it. Any linear system model can be used to do a signal injection, represented here in a general kind of case. There's no loop is evident. Doesn't have to be a loop necessarily. You can choose any injection point you want, and you get different sets of second level transfer functions, all of which give the same H. So I just labeled them randomly, sub 1 and sub 2, sub to whatever number you like. All different, but all give you the same answer, whether there's feedback or not. The essential thing we want to find out is which injection configuration to use so that the second level functions have the interpretation of them that we want them to have, to be useful for design where we want to work backwards. So here's the other consequence of that. Either of the two basic versions apply even if there is no loop at all. Now I'm shifting to a different interpretation now. Here's a network, feedback or not, doesn't matter. Suppose we choose an injection point which is adjacent to one particular element, labeled Z. So I've chosen to inject an EZ test signal in series with that element Z. I kind of imagine I can pull the element out of the circuit on rubber wires. So I can inject the test signal in series just with that element and leave the rest of the circuit alone. The formula stays the same for the overall gain of the system UO over UI. H is that ratio when you don't inject any test signal. That's the original circuit. EZ is 0. H, if you null Vy, that's a null double injection calculation. You adjust the EZ in the presence of the UI to null Vy. And if you null Vy, that means there is no current in Z. But the current in Z is the same as the current I that's going into the rest of the circuit. So nulled Vy is equivalent to nulling I. Nulling I is equivalent to the element Z not being there. So H with Vy nulled is the same as H with Z infinite. If I is 0, the circuit doesn't know what's outside, doesn't know whether there's a Z there or not. So that's simply a change of definition. What is TV? TV is Vy over Vx by definition, when Ui is 0. But again, if you inject EZ, the ratio of Vy to Vx is simply the ratio of Z to the driving point impedance looking into the rest of the circuit, because the current I is the same in both impedances. So T sub V is Z over ZdP with Ui 0, and that's given the symbol Zd. So Zd is by definition the driving point impedance looking into that circuit under conditions that Ui is 0. Finally, TnV is the same ratio of Vy over Vx in the presence of Ui, so this is double injection again, but adjusted to null the output signal UO. And again, it's simply the same ratio, except that ZdP is a different value this time, because the signal conditions in the rest of the circuit are different. ui is present now, and it wasn't before. So ZDP with the output null is a different quantity designated Zn, the null driving point impedance. So those are just different interpretations of the basic feedback formula we've been talking about for the first hour and a half. And when you substitute those definitions, you see this is identical to the extra element theorem. So they're really the same thing. The only difference is the interpretation of those second level transfer functions. And it's different depending on where you do the injection. And the benefits of the extra element theorem I summarized in the introduction at the very beginning. It means you can save a lot of analysis work by using an answer you already got. That's the h when z was infinite, when it wasn't there. And you want to add a z and see what happens, and all you have to do is calculate this correction factor. That is, you have to calculate the two driving point impedances, which are very easy to do. And I also mentioned the special case. If the circuit is entirely resistive, except for one element, which is a capacitance, then if you do the injection at the capacitance, then the ZD and Zn are resistances, and the Z is an S term, is a 1 over S term, and so you get the pole and the zero caused by that capacitance directly by separate calculations. And you don't have to recalculate anything to do with the system. So that's the single extra element theorem. This can be extended to the two extra element theorem. Choose two injecting signals at two different elements, Z1 and Z2, not necessarily related, different parts of the same circuit. Now, I'm not going to go through the proof of this. This is in a paper that was published in 1988 or 89, I forget which. And also the extra element theorem and its extensions to the two extra element theorem and to the n extra element theorem, which I like to call the neat theorem. Really is neat. And as you heard in Ray Ridley's seminar this morning, Dr. Vachi-Vorpirian has written a whole book about fast analytical techniques, most of them of which are the extra element theorem. So I'm not going to go through any of the details of the derivation of that. As a matter of fact, Dr. Vorpirian has a general derivation of the n extra element theorem, whereas the derivation, he and I wrote a paper originally on the n extra element theorem, proving it by a sort of iterative method, and in his book he has a general method for doing it, and we don't want to go into any of those things here. So I'll simply state what the two extra element theorem is, where you have two elements, you do two injections, and this is the result that you get. And you don't have to look at the details of this except to notice some symmetries. First, you notice that the denominator is always the same form as the numerator. And the only difference is there's an extra subscript n in the numerator parameters. And that means that those quantities are calculated under conditions of the output null, whereas the denominator ones are calculated under conditions that the input ui is 0. So there are two different sets of conditions, but the format is symmetrical. There's another symmetry as well. Both the numerator and denominator are symmetric with respect to the subscripts, 1 and 2. And obviously, since the numbering is arbitrary, it doesn't matter which you call number 1, which you call number 2, and you'd better get the same format. In other words, if you interchange the subscripts, you better end up with the same formula. And so the symmetry is obvious in here as well. Now, in a little more detail, what that format is, notice that all of those ratios of z's are the ratio of one of the elements, z1 or z2, to one of its driving point impedances. The extra superscript there is a constraint again. Zn1 is the null driving point impedance seen by element 1 when z2 is infinite, when it's not there. And vice versa for Zn2. That's for Z1 infinite. And you notice the last term is the product of the same two ratios, except that there's a modifying factor in front, Kd and Kn. Those are called interaction parameters. Because you notice that if either of those k's is equal to 1, then the numerator and denominator factor exactly into the product of the factor for the single extra element theorem that you would get for each element by itself. So Kn or Kd not being equal to 1 represents an interaction. It prevents the exact factoring. Now, what are Kn and Kd? Well, again, you don't have to understand exactly all the details of this, except it's better to remember it in words anyway. K is the ratio of the driving point impedances for number 1 element, with number 2 short in the numerator and number 2 open in the denominator. So think about what that means physically. You're looking in from element number 1, and you get a different answer for the driving point impedance depending on whether element number 2 is 0 or infinite, short or open. Now, if it doesn't make any difference to the driving point impedance from number 1 as whether number 2 is short or open, that means there's no interaction. That means that ratio is 1. Doesn't matter whether Z2 is 0 or infinite, ZD1 would be the same in both cases, and the KD would be 1. That means no interaction. And you can think physically how this works in a circuit. If there's a capacitor C2 near the output, and there's a capacitor C1 near the input before some interstages, then there's no interaction. Because when you look in from one element, it doesn't care whether the other element is there or not, and vice versa. You notice the final symmetry here, which is perhaps a little surprising. The KD and the Kn is the same for one element as it is for the other. Again, that's a symmetry required by the fact that you have to be able to interchange the subscripts without changing the answer. It's another redundancy. Okay, now I've shown the two extra element theorem derived by extension from the single extra element theorem. I haven't proved it. I simply stated what the result is and why it's a reasonable result. And the reason I've done that is I'm going to retrace my steps now and change the notation back to the feedback amplifier interpretation. And where each of those impedance ratios came from a T, now that I've extended this to the two extra element theorem, I'm going to replace the impedance ratios with the corresponding T's again. And you see the symmetries all remain in place. But notice in the denominator we now have Ti, which is the current loop gain, with Vy nulled, and the voltage loop gain with Iy nulled, and there's a symmetry there. And the last term is a product term representing interaction. And the Kd is again an interaction term. Same in the numerator. And here are the definitions, again exactly the same as they were with the impedance ratios. and a redundancy there again. Now the definitions of these new parameters now are simply the same as they have been for the previous cases in terms of the various signal ratios. H with IY and VY nulled is the output divided by the input, both IY and VY nulled, and it's, the superscript is just a shorthand notation for that as it was before. And the same with the T's and all the other things. Don't have to write them all out again. The superscript says which quantity is null for each calculation. Those with double subscripts are now third-level transfer functions because you have to inject 3 signals in order to null 2 quantities. So this is double null, triple injection conditions. And you say, well, this is getting messier and messier all the time. It's actually the complete reverse. We've already seen that a null double injection calculation is simpler than easier than a single injection calculation. And that's always true for the following reason. If one quantity is nulled, probably some other signals are nulled as well. That's what you can call propagating the null. Any element that has a 0 signal at it doesn't affect the answer. So the answer is simpler when those elements are not present. So double null, triple injection calculations are even simpler and easier than single or null double injection calculations. The more nulls you have, the fewer quantities enter into the answer, and the easier it is to write it down by inspection. The only thing that's seemingly difficult about this process is you're not used to thinking about the kind of calculation that you do in order to do these nulled calculations. But the thing that makes it easy, again, no matter how many signals you're injecting and how many nulls you're setting up, you never have to know what the relations are between those injected signals. All you have to use is the fact that the nulls exist, which is equivalent information. That's what makes it easy. That's what makes the answer simple. Now, if you haven't heard me talking at length about this in the previous seminars about extra element theorem, and I always say at this point, you probably don't believe me right now. But when you've practiced it a little bit and really think about this special kind of logical progression that you have to make to do these calculations, that's the only thing that's strange about it. You're not used to making that kind of calculation. But as soon as you get used to the idea and get confident in doing it, then I think you will agree that these are, in fact, easy things to do. And the fact that Dr. Volparian has written a whole book full of innumerable examples about this should help you along the way quite a lot. Okay, now we're getting to the useful answer. The original formula is still the same. The difference now is that if you do injection of 2 test signals instead of 1, then the definitions of the T and the Tn have more terms in them. And notice that each of them has 2 versions that I put at the bottom. One of them, the first one is the one I've shown already. There is an interaction term which is additive. But you can factor that, even if the Kd and the Kn are not 1. And the right-hand term is the factorization of that result. And that's exact. There's no approximation in there. It's again just a matter of whether you want the extra term to be additive or whether you want it to be a multiplier. Again, there are occasions where either one of them can be more useful than the other. One more thing about the interpretation, which is really all you need to remember about this one. The KD and the KN are the only parameters that involve the T ratios with the Vx or the Ix nulled instead of the Vy or the Iy. So what I've done here is I've started with a definition of 1 over Ti with Vx nulled, which is 1 over Iy over Ix with Vx nulled. I just turned it upside down. That's an inversion of the ratio. And that itself you could define as a Ti Vx reverse. Because a transfer function is interpreted by saying the denominator is the driving signal and the numerator is the dependent signal. That's by definition. So the inversion of Ti with Vx nulled can be interpreted as a reverse current loop gain. Similarly with the TVIX. Again, the symmetry holds all the time. 1 over TVIX could be interpreted as a reverse voltage loop gain. Now you're wondering why we're bothering to do all this. Because when you substitute that into the definitions of the KD and the KN, you get the product of two terms. But again, the interpretation in words is easier to remember. The K, whether it's KD or KN, is equal to the product of the forward and reverse current loop gains, and it's also equal to the product of the forward and reverse voltage loop gains. It's a redundancy. And that says for any general linear circuit model, the product of forward and reverse current loop gains is equal to the product of the forward and reverse voltage loop gains. Now notice the reverse loop gain is a new quantity in all this game. We haven't brought that into it before. But when you use the double injection version, you find that the overall T and the overall Tn are made up of combinations of the voltage and current loop gains, but there's that interaction term as well. And the interaction term is proportional to KD or Kn, and that means that the product of the forward and reverse loop gains gets into the act. It modifies the result if it's not zero. Now, if there is no reverse loop gain of either voltage or current, the product term disappears. But this is how you incorporate that non-ideality. And this is exact. You hope the result is going to be small. And maybe it is and maybe it isn't, but in either case you'll know what it really is. Let's go back to the same example we did earlier with a non-ideal voltage injection point. That is, the Ri is on the right of the injection signal. Now, we found that doing voltage injection only gave you the wrong answer. So now let's do the dual injection, both voltage and current, using the extended formula. Inject both a test voltage and a test current, and you can now null two signals simultaneously, and the two signals we've chosen because of the injection point is Vy and Iy. And they are the error voltage and the error current. Now remember, with only a single injection, if you nulled one of the error signals, the other one wasn't nulled. But now with two injected test signals, we can inject both, we can null both simultaneously. And that's the condition we want to set up so that VO over EI is equal to H infinity, the reciprocal feedback ratio. That's the interpretation we want to put upon the gain under that condition. So we choose to inject both voltage and current at the error summing point, such that Vy and Iy are the two error signals that we want to null. And here it is. we assume EZ and JZ have been adjusted in the presence of EI, triple injection, and we have nulled IY and VY. We don't have to know what those adjustments are. All we need to do is use the fact that VY and IY are both 0, start with EI, follow it through to VO, and what answer do you get? And the answer is R2 over R1, because the current in R1 is EI over R1, because VY is 0 at the right-hand end. All of that current goes through R2 because the IY is nulled. So the voltage at the output end of R2 is the drop in R2 because the voltage at the left end of R2 is 0. So that's why the answer is R2 over R1, and that's the answer we want to get. So now we've set it up that H with IY and VY nulled is going to be equal to the H infinity that we wanted to get. Now we want to calculate the T. The T has several contributors now, TI and TV and an interaction term. But they're very easy to calculate, simpler than for single injection. Now the EI is 0 for this condition. You inject EZ and JZ and adjust them to null the VY. What's the current ratio? You start with IX, it goes through RI, so the VX is equal to RI, so RI is out front. Multiply that by the gain of the op amp, that's the GM. That gives you the current going into the output. That's a current divider. Some of the current goes into RL, some of it goes down the R2. The ratio that goes down the R2 is that factor which is shown at the end. Now VY is 0, that's why that ratio is very simple. It is a plane divider. The left-hand end of R2 is virtual ground. So that is the current divider ratio, and the current IY is the current that's going through the R2 because there isn't any current in R1, because R1 has no voltage across it. So this is the logical sequence of steps that you go through to write down null double injection, in this case double null triple injection results by inspection. Very simple to do, very simple answers. Just a matter of getting used to the procedure. Here's the TV. Double null no. EI is 0 again, so it's double injection. And you null IY this time. Go through the same process. VX is the starting signal. It gets multiplied by GM. And we want to know what the VY is. That's a divider with RL on the right and R2 plus RL plus R2 plus R1 on the left. And VY is the voltage across R1, so R1 is the final multiplier. Again, simple, single path, straightforward calculations invoking the fact that the null exists. Very easy to do. Now, what about the interaction term? We have to find TI with VX node. So that is a double injection condition with EZ and JZ again. If VX is null, IX is going to be 0 as well, because there is no reverse transmission through the op amp according to this model. If you represent it with a two-port network, there is no reverse dependent generator in this model. So IX is 0, and IY is not 0, so TI with VX null is infinite. So the reverse current loop gain is 0. But that's a special case for this model. But if it weren't a 0 reverse gain, it's just as easy as a calculation to get it. Find out what it is. Not difficult at all. Same is true for the reverse voltage loop gain. That's also 0. And you can go through the detailed argument, as I did here, or you can invoke the redundancy. If there's zero reverse current loop gain, then there'd better be zero reverse voltage loop gain as well. So finally, you get to plug in the expression for T. The third term is zero, no reverse loop gains. And the T is the reciprocal sum of the current and voltage null loop gains. That's just like parallel combination of impedances, with the same consequence. Whichever contributor is smaller dominates the result. Plugging in the answers we got separately, you get the final result. The loop gain is 39.2 dB, and it's exactly the same as the value we got for the ideal voltage and current injection points. So using dual injection at a non-ideal point gives you the same answers that you want if you could get to an ideal injection point. But again, in any practical circuit, there is no such thing as an ideal injection point. Every active device model whose basic element is a dependent generator, that dependent generator always has a non-infinite impedance across it. That's why the collector base transition layer capacitance of a bipolar transistor always gets into the act, and the corresponding drain gate capacitance for an FET. Those elements are never zero in a real model, and they often control the entire response. So it's important to be able to include them in the result. These are the null calculations now for the Tn. Same sort of process. In fact, it's even easier in this case because two of them are zero this time. I won't go through the detail. You can follow that on your own. Tn is Gn times R2. Very simple result, built up from three separate simple calculations. Here's how you implement this in the Intersoft ICAP4 circuit simulator. This is a GFT template that does dual injection. Actually, it's called coupled injection. It injects both EZ and JZ. The program does up to 13 separate simulations to find out all these second and third level transfer functions. It does the post-processing calculations and gives you the second level and the first level results, Bode plots, magnitude and phase, does the whole thing, and it takes a matter of seconds. Here it is. Remember, this is a non-ideal injection point being used now for coupled injection of both voltage and current. And the answers are exactly the same as they were for all these transfer functions as they were for the ideal single injection. I've already shown that the General Feedback Theorem, which is what this last thing really is, I haven't used the name yet, and the two extra element theorem are really exactly the same thing, just a matter of interpretation of what the transfer functions mean. And it doesn't matter whether there's feedback or not. So you could call the combination of the two a general network theorem. So the general theorem says any first level transfer function H, again that's voltage gain, current gain, transimpedance, input impedance, output impedance, whatever you like, can be dissected into three second level transfer functions, H infinity, T, and Tn, or a fourth one because of redundancy, the H0. expressed in terms of third level transfer functions. That's the separate voltage and current ratios with one quantity known, calculated under certain single injection, null double injection, and or double null triple injection conditions, and they're all very easy to do. Now we get to the point where you have to make some choices. An injection configuration is defined by which test signals are adopted, whether it's a single voltage, a single current, or both, and on where you stick them in. The combination of those several things defines an injection configuration. Different injection configurations produce different sets of second level transfer functions, but each set combines to give the same answer for the overall result with no injection. So the question comes down to, how do you choose an injection configuration so that the second level transfer functions have the interpretation that you want them to have? Because there's no point in getting a result if you don't know what they're telling you, if you don't know what the interpretations mean. This just summarizes the Intersoft simulator properties. And we won't stop to see all this. There's a whole bunch of them to represent all these possible combinations of single and double injection. And double injection includes two voltages or two currents, as well as one of each. And the overall transfer function H is a voltage ratio, current ratio, transimpedance, etc. So each one has a separate template. And all you do is connect that template into the circuit. And that's where the hard part comes in. Where do you connect it, and what does it mean? I already said this, it runs up to 12 simulations. The 13th one is simply the original gain with no injection at all, as a check on whether the formula gives you the right answer. This is a table of the results. Dual voltage current, current, voltage, voltage. Now here's the value of all this. The general network theorem enables the second level transfer functions to be determined directly in terms of the circuit elements. That's what I've done in the little example so far. Either symbolically or numerically by using the Intersoft templates. They all produce the same first level transfer function H, but in fact, you don't really want to plug them into the formula to find the H. It's the second level transfer functions themselves that are the useful things to know for design purposes. That's why you have to choose an injection configuration so you can interpret what they mean. Because they're the things you're going to design individually to make the H come out to meet the specifications. So you have to make the crucial choice of injection configuration. Now, again, this is summarizing the two interpretations. The T's and TN's represent return ratios of specific elements in the system. H infinity represents the transfer function when one or both elements are absent. Then you can call it the extra element theorem. On the other hand, you can make the T's and TN's represent loop gains, which are also called return ratios. Return ratio is the sort of formal designation that Bode used in his famous book. H infinity represents H when both loop gains are infinite. The GNT is then appropriately called the General Feedback Theorem, the GFT. And now for the first time I've really defined what that theorem is. It's that formula when you use double test signal injection. To implement the EET interpretation, you choose a test signal at each element whose return ratios are to be determined. Those return ratios are the Z over ZD, etc. To implement the GFT interpretation, the test signal configuration has to meet two things. You've got to inject inside the major loop, but outside any minor loops. Now, again, almost every practical circuit has more than one loop. The major loop, by definition, is the one that you purposely design into it, where you feed the output signal back to the input in order to make the closed loop gain what you want it to be. But in the forward path itself, every amplifier stage has a local feedback loop because of that collector base capacitance. Those are minor loops. Now, you don't want to choose a test signal injection point inside the minor loop, because that messes up the interpretation of the gain of the stage. If you do that, it makes the collector base capacitance part of the feedback loop, and you don't want that to happen. You want to keep that separate as part of the forward loop. So you control, by means of the choice that you make of where to inject the signal, you have to inject it judiciously, inside the major loop, but outside any minor loops. And second, you have to choose an injection configuration where the two signals, or one or two signals that you want to know, are the error signals. If you inject somewhere else in the loop, nulling IY or VY, which is next to the injection point, does not necessarily mean you null the error voltage or current. Not necessarily. So you want to choose an injection point where it does null the error voltage and error current. Well, we're just about back to that first example now that I showed at the very beginning in order to demonstrate that there is a problem with some methods of feedback analysis. This is that two-stage amplifier again with both C1 and C2 present. And I did single current injection and got the wrong answer. It should have had two poles and a right and a left half plane 0. And that's not what you get. But now we know this is a non-ideal injection point, so we can do coupled injection, voltage and current, at the non-ideal point still. Now you can do this with the Intersoft process and get the answer right away. And that's how you get the right answer. I showed the right answer at the beginning, but said this is our objective, is how do you get that? This is how you get it. In coupled injection, both voltage and current. So we solved that problem. But there's another problem. You don't get the right H infinity this time. Now, I guess I have to qualify my words here. When I say you don't get the right answer, what I really ought to say every time is, the answer you get is right for what you calculated, but it isn't what you wanted it to be. We wanted H infinity for this circuit to be flat, because the resistive divider network is a flat transmission. In fact, in that circuit, R2 and R1 constitute the divider ratio. The ratio is 10 or 20 dB flat. So H infinity for that circuit ought to be flat at plus 20 dB. And the H infinity is the top graph in that picture, and it's not flat. So we got the wrong answer. We got the right answer for T. That's fine. Phase margin is 87 degrees, as a matter of fact. But we get the wrong answer for H infinity. Why is that? It's because the injection point met the first criterion. It's inside the loop. It doesn't meet the second criterion. Nulling IY and VY for that injection point does not necessarily mean that both error signals are null. Go back again. Why is that? If you null VY and IY, you're not nulling the error current, which is the current through the 10 ohms, and you're not nulling the error voltage, which is the voltage across the 50 ohms. That's because even though VY and IY may be zero, the collector current, or the drain current of the first stage, is the same as the current through C1. It's not zero. So that's why the error voltage isn't zero, and the error current isn't zero either. So this was an okay injection point to get the right loop gain, but it's not an okay injection point to get the right H infinity. And the Tn will be wrong as well. It has to be wrong. Because when you plug them either set into the final answer, it's got to be the same. So if the T is the same for both injection points, and the H infinity is different, then the Tn has to be different as well. Okay, so this is where you have to do the injection. At the error summing point itself, which is where I had it in the earlier block diagram models. It's coupled injection again, both voltage and current, and you choose the configuration so that Vy is the error voltage and Iy is the error current. And it's inside the loop, so it satisfies both criteria. Now when you calculate H infinity, what do you get? You start with EI, that's the driving signal. Vy is null, so EI appears across the R1. But Iy is nulled as well. So the current in R1 is the same as the current in R2, and therefore the output voltage is the reciprocal divider ratio, which is the 1 over K. And that's the answer you want to get. Before we continue, I want to make a diversion to explain the device models that I've adopted in all the circuit diagrams. The intent is to show that both the BJT and the FET are charge-controlled devices, and therefore should be represented by the same equivalent circuit model. The basic operation of the BJT is exactly like the FET. Output current is controlled by input charge. Input current only flows when the controlling charge is being changed. Externally, the base emitter terminals behave as a capacitance, known as the storage or diffusion capacitance. Positive base current charges up the diffusion capacitance, turning the collector switch on. Negative base current discharges the diffusion capacitance, turning the collector switch off. There is, however, one significant difference between the BJT and the FET. In the FET, the positive controlling charge and the negative controlled charge are separated by the insulating layer that constitutes the dielectric of the gate capacitance. In the BJT, the positive controlling charge of holes and the negative controlled electron charge occupy the same physical volume, the active base region, which constitutes the base diffusion capacitance. Since the holes and electrons both exceed their thermal equilibrium densities, there is a net recombination of electron-hole pairs. This is illustrated here by a little explosion, as an electron and a hole disappear by recombination. Now, the reason I showed this little excerpt is to show that both devices, the BJT and the FET, are essentially the same. They're both charge control devices. The input capacitance is an essential component of the model, because you have to stuff charge in to turn it on, you have to yank it out to turn it off. When you charge up something, that's like a capacitance. The faster you want to turn it on or off, the faster you have to supply and withdraw the controlling charge. It takes a large transient drive current. And that's exactly the same in the FET as it is in the BJT. The only difference is, in the FET, once you've stuffed the charge in there, it essentially stays. In the BJT, it doesn't stay. It leaks away because of recombination. So if you want to maintain the same controlling charge, and therefore the same output current, you have to maintain the controlling charge by constantly replacing at the same rate that it gets lost by recombination. So the model ends up having a resistance in parallel with the input as well as the capacitance. So these are the essential elements of any active device. By any active device, I mean a BJT, an FET, or a TUBE. They're all basically the same. The difference is only quantitative. That resistance on the left is essentially infinite for the tube and the FET, and it's not infinite for the BJT. I think it's unfortunate, because of historical reasons, that we have three different sets of terminology. Now that we recognize they're all basically the same, it would be nice to get rid of 2 out of the 3 sets, or better still, a combination. The selection that I vote for is collector and emitter and gate for the control. You want a dump grid because no one cares about tubes anymore. You want a dump base because that's a complete anachronism for modern BJTs. The original transistor was a point contact transistor, in which the collector and emitter were metal points stuck down on a slab of germanium. That was the base, because physically it was most of the device. But the point contact transistor was eclipsed within a year by the junction transistor. And the geometry of the junction transistor is quite different. The base is the smallest part of the whole thing. In fact, it's hard to find it to stick a wire onto it. So, but the terminology, unfortunately, has stuck ever since. So I don't expect that my suggestion of calling any of the 3 devices or describing it as a gate controlling current between an emitter and a collector, that's my choice, but I'm sure it won't catch on. But that's the choice I put in this picture now. Now, these are the 3 basic elements, as I said. Now, it's useful sometimes to make some manipulations of the model. In this one, VGE, V gate to emitter, is considered the controlling signal. So the current generator is a transconductance generator. In this one, I've reflected that base resistance into the emitter leg, or the gate resistance, I should say, into the emitter leg. And now the VGE is still the controlling voltage, but I can choose the emitter current to be the controlling signal. And the collector current is alpha times IE, where alpha is almost 1. Now still this model applies to either a BJT or an FET. The only difference now is whether alpha is equal to 1 or not. If alpha is a bit less than 1, it represents the BJT. The collector current is not quite equal to the emitter current, and the gate current is 1 over 1 plus beta times the emitter current, which is a very small fraction. Base current, the gate current is not 0, but it's very small. On the other hand, if you make alpha equal to 1, this is now an FET model. And notice that what the model tells you is that the gate current is 0. Because the collector current is exactly equal to the emitter current if you make alpha equal to 1. Same model, but it's now an FET, and the only difference is whether you make alpha 1 or not. So it draws everything into one model, which is appropriate since they all really work the same way. And the reason I went into this diversion is that that's the model I've adopted here in the earlier ones, but I didn't stop to mention it. I've shown alpha explicitly in both of these device models. But in the calculations that I'm doing on this model, I'm going to make alpha equal to 1. And it works. The model is the same, whether these are BJTs or FETs. And all of the techniques and all the stuff I've talked about today and all the stuff that's been written for umpteen years beforehand, it's all the same, whether they're BJTs or FETs, except for that one tiny difference. Okay, here's the results of the simulations of that model with the coupled injection at the error signal summing point. H infinity is flat at 20 dB where we wanted it. The loop gain has 2 poles and the right and the left half plane 0 where it should be. And the closed loop gain H peaks up a bit and levels off again just below 0 dB at infinite frequency. Now, I haven't mentioned much about what the final H is yet, but notice I did mention that the loop gain had a phase margin of 87 degrees. Therefore, the apparent peaking in H is nothing to do with an inadequate phase margin. Normally, you'd make that association. Closed loop gain peaks up before falling off. Oh, we don't have enough phase margin. Not true. Phase margin is fine. Loop gain is fine. Where does the peaking in H come from? It comes from the non-idealities. It comes from the H0 or the Tn, whichever one you want to use to represent it. Here are the components of T. Remember, it's the reciprocal sum of 3 terms. 1 over Ti with Vy node, 1 over Tv with Iy node, and the interaction term. If you plot them separately like this, you know that the triple parallel combination is dominated by whichever one is smaller. Well, no question in this case, the Ti with Vy node is always the smallest one at any frequency. That means that's the one that determines what the T is. The others don't matter. So the third term is negligible, and so is the second. Only the first term in the result is important. Here's the crucial result that tells you why the output actually peaks up, even though you have an adequate phase margin. The D, the discrepancy factor, doesn't show any peaking, which it shouldn't with a phase margin of 87 degrees. The H infinity D, therefore, doesn't have any peaking either, because the H infinity is flat. So it's the other term. Here's the H0 representation. The H0 is not 0. H0 times D0 has the peak in it. So when you add that to the H0D, now you see why the H has a peak. The direct forward transmission through the feedback path in the wrong direction dominates the result at the higher frequencies and makes the H itself have a peak. This means that if you did a step function response, you don't get a huge ringing overshoot because the phase margin is fine. In fact, you get a huge undershoot. But we don't need to go into that. The point I want to make here is the direct forward transmission term, a non-ideality, dominates the result. Now I have to admit that I chose a set of numbers in order to exaggerate that. But that's okay. The important thing is you get exact answers very easily and quickly. And you can check then whether something is negligible or not. That's really the only reason for doing it. You don't have to guess or assume. Now, I said that the transfer function H can be any function of a linear system model, including output impedance. So let's use it to calculate the output impedance of this same two-stage amplifier. H now becomes ZO, but the formula is still the same. How do you set up the transfer function ZO? You stuff a current into the output and observe what voltage is developed across the output. That's a self-impedance. So, here's the circuit again, and you stuff a current JI into the output. And you look at the voltage VO which is developed, and the ratio is ZO. That's the quantity you're looking for. So you select the appropriate template. This is called GFTH. Use the same injection point, because you want to keep the same loop gain. Now for voltage feedback, the H infinity term is 0. That's for gain, voltage gain, that's the important one that you want. But for output impedance, it's 0. Why is that? Because we know voltage feedback lowers output impedance. If you have infinite loop gain, the output impedance goes to 0. So that's why the H infinity is 0 when the H infinity is ZO. So the only term left is the other one. And this represents the usual result that everyone remembers. Output impedance equals open loop output impedance divided by 1 plus T. That's the conventional result. And here are the components that you get from the simulation. ZOO is the open loop output impedance. 1 over 1 plus T is the weighting factor. The product of the two is the closed loop output impedance. As expected, it's very small at low frequencies where you have a lot of loop gain. As the loop gain goes away, the output impedance rises. Notice that that means the closed loop output impedance looks inductive. And I found out many years ago when I was doing similar measurements on the old 709 op amp. If you remember that original historical thing, it does indeed have an inductive output impedance. The output impedance rises to a maximum where the loop gain crosses over. And it joins the open loop value because when the loop gain is gone, the closed and open loop values are the same. So that's why the output impedance falls off again at higher frequencies. Enough for that two-stage amplifier. Now, to finish up, I want to tell you about this more practical kind of problem. The Darlington follower is known to be unstable for certain values of load capacitance. The design problem is to select a damping resistance so the follower is not only stable, but has maximum peaking specified regardless of the load capacitance. That's your design objective. How can we use the GFT to look into that? Here's the linear model. Cascaded emitter or source followers. This time the C1 and C2 represent the basic charge control capacitors, which I didn't put into the previous example, but I could have done. The simulator will handle any number of those, of course. And to make it easy, I've assumed that we have FETs, not BJTs, so the gate current is 0 in both cases. Alpha is 1. That's the basic model. Now, it's worthwhile before we start doing any analysis to figure out why you have a potential instability in the first place. So I stripped this down to the essential features. We've got a load capacitance CL. Why is that model potentially unstable? Well, one way to look at it is consider the first stage only. Do a little analysis on it to find its output impedance, ZO. Doesn't take much algebra. Don't have to go through the steps right here. ZO gives you the expression underneath, which can be put into factored pole zero form. And you see you have a 1 plus S term in the numerator. So the S term represents an inductance. The definition of that inductance is it's equal to C1 RS times R1. What that means physically is if you look into the source of a source follower, the signal resistance RS looks like an inductance over a certain frequency range. That's impedance reflection factor. The impedance reflection ratio is frequency dependent because of the C1. That's what makes the RS convert to an effective inductance. So there's the equivalent circuit model that represents that equation. Now look at the other stage and ask what is its input impedance, ZI. Again, it's a reflection question. And when you write the expression, which is simple enough, ZI reflects the CL into a negative resistance. So the answer is you get a capacitance in series with a resistance where the resistance is negative and is related to the load capacitance. So when you add the model, there's the negative resistance with the capacitance. Now you put the two stages together, and now you have a negative resistance oscillator. Well, it may or may not oscillate depending on which of the damping resistances is dominant. Basically, you have two series damping resistances and one shunt resistance. And one of the three is negative. So it depends whether you get an instability or not. Now that's the physical interpretation. What can we do about designing it so we make sure it doesn't go unstable? But more than that, we don't want any excessive peaking in the transfer function. The crucial step in applying the GFT is the choice of the test signaling configuration. So what do we do this time? The purpose of the Darlington follower is to give you a voltage gain of 1. So we want H infinity to be 1. So we want to choose an injection configuration that will make HIY, VY, whichever one we want, equal to 1. So choose an injection point so that the Vy is between input and output. So if we null Vy, we will get unity voltage ratio. That's why we choose an EZ injection with the labeling as shown here. Vy is between EI and the output. EZ can be adjusted relative to EI in order to null Vy. What about IY? Do we want to null that as well? No, we don't this time. IY is the only current that drives the output. If you nulled IY as well, you wouldn't get any output. So we don't want to do coupled injection this time, we want to do single voltage injection. Because the only condition we want to get is a null Vy. To find T, we make EI 0 and evaluate Vy over Vx. If Zx is the impedance looking into Vx and Zy is the impedance looking into Vy, Vy over Vx is equal to Zy over Zx, because the same current flows through Zx and Zy. So T is equal to Zy over Zx. That's simply the ratio of the impedances looking forward and backwards from the injection point. The same old ratio that messed up the answer we wanted in the previous examples. The impedance ratio affects the value of T that you get. In this case, it's the only value, it's the whole thing. This ratio is T. Now, Zy is simply the load capacitance. Zx is a fairly complicated impedance because it looks back through the two devices. But the T that we want is simply Zy over Zx. Now what is Tn? Tn is Vy over Vx if we inject Ez in the presence of Ei and null the output. But if you null Vo, Vy is then equal to Ei. And if you null the output, there's no current through Cl. That also means there's no current going back into Zx. So Vx is 0. So Tn is infinite. So the formula reduces to H equals T over 1 plus T, which is just D, and T is Zy over Zx. Now we can figure out a lot about T before doing a simulation. Zx, that's the impedance looking back, has two poles because there are two reactances in the Zx. If you look at zero and infinite frequency, which is what I call doing a mental frequency sweep, if you look back into Zx at zero frequency, the two caps are open. What impedance do you see looking back? You just see the R2. What impedance do you see looking back at infinite frequency? The two caps are short. And Ei is 0 for the impedance Ex. So you see Rs. So you know that the Zx is flat at 0 frequency and it's flat at infinite frequency, and therefore because it has two poles it must have two zeros as well. But we also know that Zy is simply 1 over SCL, which is a single pole. So the ratio T has 3 poles and 2 zeros. That's a pretty complicated function. And that's why we get a potential instability. Here's the answer by simulation. H infinity is 0 dB as intended. That's always the first thing we want to check. Make sure we didn't make a mistake somewhere. T, magnitude of T, this is calculated for a CL of 1 picofarad. It's got one pole at 0 frequency, so it starts out on a -1 slope. Then it has a little peak and it goes into a triple slope, because we got two poles at the same frequency with a high Q. So that little middle region is a triple slope. Then the two zeros come in further up. So the two zeros cancel two of the poles, leaving you with a one-pole final asymptote. And look what the phase does in between. Real gyrations there. It starts out at -90 because of the single slope. And then because of the additional double pole it encounters, it plummets down to almost 270. But then the zeros start bringing it back. And the two zeros bring it back to -90 degrees at infinite frequency. Now with these numbers, the crossover frequency is close to the triple slope part. And the phase margin is minuscule, 7 degrees. That's why the H has a substantial peak in it. I don't remember just what the value is, but you see this is a pretty condensed scale, so the peak is pretty big. Now, for design purposes, the load capacitance has to be considered a variable. You don't have control over that. What is the effect of CL upon the loop gain? Well, the value of CL shifts the magnitude of T up and down proportionately, because the ZY is just the capacitive reactance. ZX is independent of ZL. ZX is looking back into the followers. So the effect of changing the CL is merely to lift the entire magnitude of T up and down. The phase doesn't change. So the phase graph stays in place, and increasing CL lowers the entire magnitude graph proportionately. Now you see what's going to happen if you do it. It means the crossover frequency is going to move down. And the phase margin is going to disappear mighty fast. And when you get into the region below -180, it's unstable. So, the blue line is the original picture. Now I've increased CL from 1p to 10. That lowers the whole magnitude graph. The phase margin is now negative. It's unstable. Now if I keep on increasing it more, it'll go past the minimum point and start coming back again. And if you make the CL big enough, it'll eventually become stable again. So there's a much bigger CL, and the phase margin is still negative, but it's coming back. So there's a pretty wide range of load capacitance where the system is unstable. Now that's the analysis part. The design part is, how do we prevent this from happening for any value of CL? So what we want to do is put a series damping resistance in. Put a damping resistance RD added to ZX, so the maximum phase lag at any frequency is less than 180 degrees by some desired phase margin. And it's not sufficient just to make it stable, you want to make it stable enough. Here's the same picture we had before. For the one P load capacitors. But now start adding some damping resistance. This is 100 ohms in series with a ZX. The maximum phase lag is now considerably less than it was before, but it still goes beyond 180. So make the damping resistance bigger. Now we have a maximum phase lag of 133 degrees. That means if we were to cross over at that worst case position, the phase margin would be 47 degrees. Well, that's not great, but it's almost okay. So suppose we stay with the RD of 1,000 ohms. There it is. It's the original condition with 1,000, but now I can choose a CL, which turns out to be 0.78 puff, which makes the crossover frequency occur at the frequency of maximum phase lag. Now, any different value of CL is going to move it away from that worst case and make the phase margin better. So I've set the worst case phase margin regardless of the value of load capacitance. And that's the design objective. This is a blown up scale of the same situation. So I've got a peak of 2 dB, which goes with a phase margin of 47 degrees. And you can decide whether that's enough or not. The point is you have a unique process by which you can fix that design. That's the end of that example. So it's time to summarize everything now. Conventional approach. You have a feedback block diagram. As I said, this is always the thing you think of first. You draw the diagram, or at least you have it in your mind. And that's all there is to it, except that you replace the boxes with unidirectional triangles, arrows. Why do you do that? Because every picture you've seen looks like that. And you tend to forget that this implies the constraint. The model is now unidirectional and is therefore not accurate for most practical cases. You inject a test signal in the forward path somewhere, and we have many times gone through that process. You don't want to disconnect the feedback path because that upsets the loading. You inject the signal where there is no loading, which is an ideal injection point, and you have to inject coupled test signals if it's a non-ideal injection point. But still, you don't get the right answers because reverse transmission is ignored still. Now, the books have an alternative. They get to this same point that we've just reached here. And they say, the model isn't correct. So let's represent each path by a two-port network. And for this feedback configuration, which is series voltage, series shunt voltage, the H parameter boxes are the appropriate ones. This requires 4 different sets of two-port parameters for the 4 feedback configurations. And it still isn't clear how to account for the reverse loop gain, which is now in there. Because you see, you've got a dependent generator in both directions. So the model is correct to that extent, but you still don't know what to do with it. How do you define loop gain when it goes both ways? You don't know. And what is done in the books is the reverse transmission of one path is simply added to the forward transmission of the other one. Or it is simply ignored. Well, that's okay to do that, but there's a fatal flaw in the whole process. Even this model is not accurate, because the forward path model ignores totally common mode gain. Because look, the model is drawn as a 4-terminal network, not a 3-terminal network. If you pull the two inputs up and down together, that's a common mode signal. But this model says there's no output. But if you do that with a real forward path, you do get an output because of common mode gain. So the model itself is deficient, whatever you do to account for the forward and reverse transmissions. So that's a loose end too. There's only one of the 4 models which is correct, the only one that doesn't require common mode gain, which is the parallel-parallel connection. So the disadvantage of this method is the model itself is inaccurate for 3 out of the 4 connections because you ignore common mode gain. But whatever, the real disadvantage is much worse than that. This is essentially totally useless for design. The circuit elements are buried inside the 2-port parameters, which are themselves buried in expressions for closed loop gain and loop gain. You haven't a hope of working that backwards in order to correct values or change the result in the direction that's under your control. It's not design-oriented analysis. It's simply useless analysis, whether it's right or wrong. So this is the approach I'm recommending. Same original model, but note the boxes stay there, not arrowheads. They're bidirectional. It's the real circuit. And you inject coupled test signals at the error summing point. That satisfies both criteria. It's inside the loop, and nulling the IY and the VY also nulls the error voltage and the error current. The results include reverse transmission in both paths. Therefore, it also includes reverse loop gain. It's exact. You can make approximations if you want. You can see whether they're good or not. All 4 second-level transfer functions are produced, either numerically if you do it with a simulator, or symbolically by null double injection and double null triple injection analysis. And I hope even by now you're not put off by those words. The second-level transfer functions combine in the GFT to produce the first-level result. But as I've said, you don't really make the substitutions. It's the second-level ones themselves which you're interested in order to adjust them for design purposes. The result fits this block diagram. And here's perhaps the biggest shift in viewpoint of all. The block diagram is the answer. It's what you get by solving for those transfer functions. They fit this diagram. In other words, this diagram is not assumed to begin with, and you try to calculate each box separately from the circuit. That doesn't work because it doesn't properly handle the non-idealities. By this method, the diagram comes out of the answer, and you get the correct results for all those transfer functions. It's a result of simple, straightforward, exact calculation, not the result of initial assumptions. The second-level functions are obtained directly in terms of the circuit elements. That's the only way you can do design-oriented analysis, which is the only kind of analysis worth doing. And I've said several times now, don't be put off by this NDI, DNTI things. They're easy. It's just a matter of practicing them until you know what to do. So I want to close with another little video clip, which is what I say at the end of my structured analog design course. It has a little exhortation and incentive at the end of it. All I'm saying is, let's try to reduce the size of this cliff so that when you get out of school, you don't fall so far, and maybe you can maintain continuity of slope. Avoid a discontinuity of the first differential. That would be nice if you could do that. Well, unfortunately for all of us here, this is too late. So what I'm saying is, even if you're starting down here, you can still increase the slope. Now, nothing's free, no free lunch. There are prices you have to pay to get the benefit. And in this particular case, if you're going to get the benefit of these techniques and shortcuts that I've been telling you about, you're going to have to practice them. And there's no way around that. You can't do it all at once, and you can't become instantly capable and competent in all these methods, which is the same thing as saying, if you have to read a technical paper that's written in Russian, it's too late to start learning Russian. Or, in other terms, the funeral directors are always telling us to plan ahead. And it's the same thing here. Because when you need it, it's too late to start learning it. You've got to have that practice ahead of you so you can jump right in and use it. Otherwise, it's of no value. And that's going to be up to you. But that's the bottom line.